In this video, we're going to talk about an assortment of other rotational concepts that aren't going to play out too much in this chapter, but I want to introduce them here, and we'll probably talk about them more in the chapters to come. But there's more analogies from the linear world to the angular world that I want to talk about. Okay, so for example, force in the linear world. Okay, and the idea is what force becomes in the linear world. Well, you're probably on the slide right now. It's the slide that says torque, right? So torque is like the angular force, all right? And to be specific, torque is actually force times the radius, right? How far you are away from turning an object times sine of theta, right? So let's say that, again, I don't know, let's say it's a helicopter blade just for consistency's sake. Okay, and so let's say I want to get this thing rotated. I want to start to get it to accelerate. I want to give it an angular acceleration. Then I need a torque to do that. Just like to get a linear acceleration, I need a force. All right, and that torque is, well, if I apply a force here at some angle, theta, at some distance r away from the axis of rotation, okay, then that's the torque that I get. I get a torque equal to how strong that force is, how far from the axis I push it, times sine of the angle at which I apply it, right? Because here's the thing, sine of 90 is biggest when sine of theta is biggest when theta is 90, right? Which makes sense because if I'm pushing this at a 90-degree angle, I'm getting the most bang for my buck, right? But if I'm pushing here, the smaller this angle gets, like if I'm pushing a force in this direction, not all of that force is used to actually rotate it. Some of that force is directed in just pushing the blade against the hinge, right? Not very useful. So this sine theta is my way of saying how much of the force that I'm applying is actually perpendicular to the blade and is actually getting it to rotate. Okay, so all of these matter. Okay, we're going to talk about this much more in the next chapter in rotational dynamics, but I want to introduce this concept that in order to get a linear acceleration, I need a force. In order to get a rotational acceleration, I need to use a torque. Okay, all right. Turns out that there's also an interesting analogy for mass as well. Mass in the rotational world is not just m, okay? Because not all masses are created equally when it comes to rotation. And I'll explain what I mean by that in a second. So mass becomes something in the rotational world called rotational inertia. Man, that is squeaky. Wow. Okay. And here's the thing. Rotational inertia is proportional to two things. Why do I even use this pen? I don't know. Can't explain it. Rotational inertia is always proportional to two things. It's proportional to mass, which makes sense, right? Obviously, the mass in the rotational world, this is the mass in the rotational world, should be proportional to mass. But it's also proportional to r squared. In other words, how far are you from the axis of rotation? Okay, so let's take an object like again helicopter blades, right? Let's say this thing weighs m, right? But all that mass is limited to a small little r, right? That's kind of easy to turn, right? A small little r is easier to turn, right? If this isn't too big, right? If this is kind of like a small number. But what happens if you have the same amount of mass, but it's a much bigger blade? Okay? The fact that so much more of this mass is distributed farther away from the axis actually makes it harder to turn, right? So this will have more rotational inertia. In other words, more resistance to motion if the mass is spread out at a farther distance from the axis of rotation. Okay? So if you go to the slide that says moment of inertia, you'll see a little chart that has the different moments of inertia of different objects, all right? And you'll notice that the more the object has mass concentrated farther away from the axis of rotation, the more rotational inertia you have. It's also called moment of inertia, as you can see from the slide. So rotational inertia and moments of inertia are basically the same thing. Okay? And really it comes down to, you know, the mass or the inertia of the rotational world. So, for example, a ring that is, you know, has all of its mass concentrated at a distance r away from the axis of rotation. So for a ring, the moment of inertia is going to be just mr squared, right? But for an object like a rod, right, straight through the middle of that rod, okay, you are going to have a moment of inertia of 1/12 ml squared, where L is the length of that rod. Okay, so as you can kind of see, right, this will have less rotational inertia than this will, because the ring has all its mass concentrated at a distance r. Okay, and the rod, the mass is distributed throughout, so not all of the mass is focused at the ends, which makes it a little bit easier to rotate. Okay, we're going to deal with moment of inertia much more in the next chapter. And you'll see it then. Okay. The next thing I want to kind of introduce is rotational kinetic energy. Okay. And so you could have an object with no translational motion, right? It could not be going from point A to point B. It could just be rotating, and it's still going to have kinetic energy. Why? Because the molecules in it are still moving, right? Even if something's just rotating, those molecules that it's made of still have motion. They still have energy. Okay? So in the linear world, or the translational world, kinetic energy is, of course, just 1/2 mv squared, right? And rotation, you could probably guess, right, going from here to here. So this will be linear kinetic energy. And so rotational kinetic energy is going to be 1/2. What is m in the rotational world? Well, it's the rotational inertia that we just talked about, or the moment of inertia. That's I. Okay. And what is v in the rotational world? What is linear velocity in the rotational world? Angular velocity. So you just replace that v squared with an omega squared. Okay. Again, we found a new concept, this rotational kinetic energy, just by replacing the old equation with new variables, with the rotational variables. Okay? And this brings me then to this whole concept of rolling. Like, imagine I have an object that's rolling. Okay? An object that's rolling, notice it's a mixture of rotation, right? It's spinning and it's moving linearly at the same time. Kind of cool, right? So you can think of rolling, the case of rolling, as a mixture of linear plus rotational motion, right? Rotational motion would just be like, OK, so I put a pin in the middle and I spin it like a merry-go-round, right? Linear is just I push something and it moves in a straight line. But rolling, it's moving in a straight line and it's spinning at the same time. So you can say that the kinetic energy of rolling is 1/2 mv squared. How fast is its center moving? Plus 1/2 m omega squared. How fast is it rotating? Okay? So that's the kinetic energy of rolling. Again, we're not going to use these too much in this chapter, but I want to introduce these concepts to you and basically reinforce this notion that everything in the rotational world is just analogous to the linear world. We're just replacing our old variables with the variables of the rotational world. Okay? It's like 2 dimensions that I can just jump in and out of depending on what's happening in the situation. And now we're much more flexible, right? We can solve many more problems. We can solve straight motion problems, and we can solve rotational problems, right? And it's all good. Okay? Lastly, for this video, I want to just look at this misconception question number 2. It says, an object at rest begins to rotate with a constant angular acceleration. If this object rotates through an angle theta in time t, through what angle did it rotate in half the time? Well, what are we talking about here? What kinematic equation? It's asking about the angle with which it rotates. So it's asking about theta, right? It says it begins to rotate, so omega 1 is 0, okay? And lastly, it talks about a certain angular acceleration that's constant. So this implies to me that I would use omega 1t plus 1/2 alpha t squared. But omega 1, remember, is 0 here. It's going from rest, right? So theta equals 1/2 alpha t squared. So what angle would I move through if I have the time? Well, let's have the time and see what happens. Well, we get the same thing back, except there's this 1/4 at the bottom, right? This 2 is being squared, okay? And you get 1/4. So it'd be 1/4 of theta if it rotated for half the time. Make sense? Okay. Next up is the last video, and we're going to take another look at that Samoan Biles move in the air. And then that'll wrap up this week.